Hi guys, we're going to continue solving right triangles. This time we're introducing the trigonometric ratios. In this video we're going to talk about what the trigonometric ratios are. Then we're going to do 5 examples. So let's get started. So let's talk about trigonometric ratios. In a previous video I talked about proportional shapes. We talked about how you could take 2 proportional triangles and with one triangle find the missing sides of the other. So if I do that here, I could set up a ratio 1/2. Then I'll put an arrow here. y/4. So y/4. And in doing so, I can cross multiply and then divide by 2, and I can get y = 2. Now that I know that y = 2, I could set up another ratio of 1.73/1, 1.73/1 to, let me set this up a little clearer, x/2. Okay, then I cross multiply and I get x = 3.46. Alright, I'm going to do this one more time. This time I'll set up a proportion 1.73/2. So 1.73/2. Then, as a result of that, we'll have to set it up x/4. Now what I'm going to do is I am going to cross multiply and solve. So I have 2 times x, which is 2x, and then 4 times 1.73 is 6.92. Then I could divide that by 2, this by itself, and I will get 3.46 again. So as discussed in that previous video, there is a multitude of different proportions I could set up. I set up 3 specific proportions for a reason. So if I take 1/2 and convert it into a decimal, I get 0.5000. I'm going back for decimal points for a specific reason. 1.73 divided by 1 is still 1.73. Then 1.73 divided by 2 is about 0.865. So here's what has been done. Instead of walking around with a bunch of little triangles, somebody a long time ago took those ratios and put them in a table. How does that help? Well, now I don't need this triangle anymore to solve for these missing sides. I can just use those ratios. And factually, it was recently discovered that the ancient Japanese, in fact, used these ratios to build their castles. And they weren't the only ones. The entire planet is built on these ratios. So let's take a look on how to use them. This is my reference angle. And what I can do is I can draw an angle out from my reference angle or the acute angle of the triangle and label this the opposite leg. Across from my right angle is the hypotenuse. Then I have the adjacent leg here. Well, if I'm looking for this angle, the opposite leg, and I have the hypotenuse, I can go to this table at 60 degrees and use this decimal. So let's take a look at what that looks like. So if I want to place any number into a fraction, I could just put a 1 underneath it. So I could take this 0.8660 over 1, which comes from dividing 1.73 by 2, then set it equal to x over 4, and I can cross multiply and solve. 1 times x is x, then 4 times 8.8660 is 3.464. So I could just use the tables. I don't need that extra triangle. The point here is that the ancients didn't walk around with rings of similar triangles to build stuff. Eventually they figured out that they could just write these ratios down of similar triangles that they commonly used and just apply those ratios to other proportions to find what they need to solve for certain lengths. We use this math today in almost every field. Trigonometry is broadly used and broadly applied. So now, let's make it even simpler. We can make this even simpler still. I can actually get rid of the trig table now, thanks to modern calculators. And what I could do is, on my calculator, I will see 3 buttons: sine, cosine, and tangent. They present as SIN, COS, and TAN. If I plug these individually into the calculator as I wrote them, so if I type in sine 60 and hit enter, I will get square root 3 over 2 or 0.8660. If I type in cosine 60 into the calculator and press enter, I would get 1/2 or 0.5000. And lastly, if I put tangent 60 in the calculator, it gives me square root 3 or, if you can't guess it, 1.7320. So now I don't even need to use that decimal there anymore. I could just replace it with sine 60. Making this whole process of solving a missing part of a right triangle, which is critical in a number of different fields of math, very simple to do. Alright, let's put it all together now. The way these abbreviations read is, this is sine of theta, this is cosine of theta, and this is tangent of theta. These ratios are derived from dividing the opposite leg and the hypotenuse of a right triangle, the adjacent leg and hypotenuse of a right triangle, and the opposite and dividing the opposite and adjacent leg of a right triangle. Theta is just a Greek letter meaning reference angle. So in this case, 49 degrees is theta, and what I'm going to do is label the triangle. So this is the opposite leg. Across from the right angle is the hypotenuse, and then this is the adjacent leg. From there, we're going to use that information to solve for x, or the missing side of the right triangle. Okay, so I have the opposite leg, and I am looking for the adjacent leg. When I look at the three ratios that I have, I see that tangent divides the opposite and the adjacent leg to create a ratio. So all I have to do here is create a proportion involving tangent. A proportion is just a fraction equal to a fraction, and I'm going to place tan with the reference angle together, as I showed you as we discussed how the ratios work. I'm going to place a 1 underneath, and then fill the ratio in the way it is made, or how it's dictated on the table if I want to keep it simpler. So I have to have the opposite leg over the adjacent leg. And the reason for that is because whatever tangent 49 is equal to, it is derived from dividing the opposite and adjacent leg. Now I'm going to cross multiply. Okay, so 1 times 14 is 14. X times tangent 49 is just x times tangent 49. Just as if x was multiplied by 2, or x times 2 would be 2x, well, tangent 49 times x is just tangent 49x, or x times tangent 49, however you want to write it. And just like we would if we had 2x equals 14 and we have to divide by 2, we are going to divide tangent 49 out to both sides. Tangent 49 divided by tangent 49 is 1, just like anything divided by itself is 1. And now I get my calculator and I punch this in so I can get this answer. It might take a little practice, but use this video to practice plugging this stuff into your calculator so that you can get that answer. I did not use the calculator until x was by itself. Alright, let's take a look at another example. So in this example, I brought the table along with us, the sine, cosine, and tangent table. I'm going to follow the same steps or algorithm. This is my reference angle. I'm going to label my triangle. So this is the opposite leg here. Across from the right angle is the hypotenuse, and then this is the adjacent leg. Once again, I have the opposite and adjacent leg, so I'm going to use tangent. If you look at how this is written out, and I put a 1 underneath here, it is telling me how to set up the proportion. There are a couple of different methods for solving these, and I prefer cross multiplication, and I'll explain why. Because in the previous example, when I cross multiplied, I ended up having to divide the tangent ratio. In this case, I don't have to do that. The cross multiplication allows me to see when I'm going to divide the tangent ratio or multiply it. Some people have that memorized. If you've watched some of my previous videos, you would know I am definitely not a fan of memorization. When I plug 12 times tangent 24 into my calculator, I get 5.34. The general rule for math, unless stated otherwise, is to go back 2 decimal places. Now, let's talk about what this number means. That number means that this length here is 5.34, and it cannot be any other length. So if this is, let's say, centimeters, this is how long that will physically be with this angle. There is no other length that leg could be with that angle and the one leg being 12 centimeters. Alright, let's take a look at the next example. Okay, so the reason why we're doing this example here is I just want you to see that not every triangle will work out to be tangent, but the procedures of the algorithm for solving a right triangle does not change for the different ratios. I am going to circle my reference angle, which is 33, and then label the opposite leg, and then this is the hypotenuse, and what's left is the adjacent leg. In this problem, I have the opposite and the hypotenuse, so we're going to be using sine. Once again, as I showed you last time, the table shows you how to set this up. Now we're going to plug into the ratio. So sine 33, because this is my reference angle, or theta, over 1 equals x over 14. Be careful. It's a common problem I see all the time amongst my students. Do not flip the ratio. Opposite over hypotenuse is how this has to be set up. If you set it up the opposite way, you are not using the ratio properly and you will not get the correct answer. That's also the reason why it's critical to label your triangle. Don't skip that step. It's very easy to get disoriented on a triangle, right triangle, once the orientation gets a little funny. Then you pick the wrong ratio, or you flip the ratio and you get the answer wrong. I'm cross multiplying here. 1 times x is x. Then 14 times sine 33 is 14 times sine 33. Since I'm talking about issues that students often have with these, another one is if we type this. If you punch down into the calculator and let's say close these parentheses, you change the reference angle to 462. The calculator will look at this as 462, which essentially means it's going around a circle, then around again. That's not what we're looking for. We want to know, and if I punch that in, let's do it this way. If I punch that in, sine 462, I get this decimal, 0.9781. If I punch in sine 33 into the calculator, sine 33, that decimal is 0.5446. These are different numbers, so that means you're going to get a different answer. This will give you the wrong answer. So just to avoid that error, I always, when I multiply, keep the 14 or whatever number I'm multiplying by in the front, because it's another very simple error to make. So when I type 14 times sine 33, I get 7.624 or 7.62. Again, let me just say one more time, just so we understand what we're doing. That means the length of this side is 7.62 and cannot be anything else with this angle and that hypotenuse. And I should also say, assuming it's a right triangle. We cannot have any other length there. Alright, let's take a look at finding an angle. Finding an angle is one of those things everybody always forgets how to do because it's extremely simple. My students hear me say all the time, simpler does not mean easy. Simpler sometimes means more difficult because it's easy to forget. Alright, I am going to follow the same steps I've done before. I have to follow this angle, so this is what I'm looking for. And that's my reference angle that I need, and I'm going to label my triangle just the same. Now, this is going to be opposite and adjacent again. The examples I found for some reason love tangent. And what we're doing here is we're going to use an inverse trig ratio. This is a dedicated button on your calculator. If you have a TI-36X Pro or a TI calculator like the one I have, oftentimes you just press the tangent button twice and that inverse sign comes up. Sometimes it requires shift or the second button. On my calculator, it's written like this, then tangent to create this. You cannot use the exponent key and put a -1 there. That does not create an inverse tangent function. This is a specially coded function in the calculator where it's using the table in reverse. So it's kind of stored information in a way. So now when I plug that into the calculator, and in my case, I have a very good calculator, so I could even use the fraction button, and I get 21.37 degrees. That is how many degrees this has to be to get this length and that length in a right triangle. Finding the angle of a triangle could be a little bit weird. Students often get confused about that tangent inverse sign. It's just a dedicated button, and then you place the division in there. Okay, so let's take a look at a word problem. I picked this word problem specifically because of this, a guy wire. All a guy wire is, which a lot of people don't know, is just a wire that holds a pole from getting blown around in the wind. They usually just kind of anchor to the ground from the top or midway up the pole and just secure the pole in place. Now, the wire and the ground, so we'll call this the ground, so this will be our ground. We'll make a 60-degree angle. Then the pole is anchored to the ground 15 feet from the bottom of the pole. So this would be here. How tall is the pole? I make this statement in the Pythagorean theorem word problems. Don't go crazy drawing pictures. Just draw a right triangle and then label it. If you are struggling with word problems, Pythagorean theorem and trig problems are a great place to start if you have control of the math, because they always start with a right triangle and you have to label them. Reading Pythagorean theorem and trig word problems could give you confidence in other word problems that you will later have to do. Now I'm going to follow the same process for solving this. Okay, so I'm going to label my sides. This is the opposite leg. Across on the right angle is the hypotenuse, and this is the adjacent leg. Oh my god, we have tangent again. So I'm going to use the tangent ratio. Well, I tell you what, if you watch this video, you're going to get pretty good at using tangent, I guess. So this is x over 15. And now I just cross multiply and solve. So that's x, then 15 times tangent 60. And now I'm going to plug that into the calculator. And let's see what I get. Alright, I get 15 square root 3. I will point out, just like I mentioned in my Pythagorean theorem presentation, if you get an answer like 15 square root 3 and it's not multiple choice, that is the answer. There's no reason to change that number. It is the most precise answer. And I would just keep it that way. Now, if you actually need to figure out how tall the pole is and you have the measuring tape, and then convert it to the decimal, that works for you. Again, trigonometry is a pillar of math, and it is definitely a worthwhile investment to get the first parts of trigonometry under control so you can advance to more advanced mathematics. Alright guys, I hope you found this video helpful.